why is an action potential not a single channel?
Isn't it based off of a whole cell? Isn't it based off of a whole cell?
Yes, what about it?
So it takes into consideration like all different channels.
Exactly. And so what channels have we talked about that it takes into consideration? Obvious, huh? Sodium, potassium, chloride. What other type in general that we just talked about? Lead, right? Any one of those, or all of them. But a single sodium channel will not produce an action potential, and the potassium channel certainly won't, because if anything, it will bring the voltage to a more negative value than what a typical action potential does. And we have defined it, that is unambiguously. It's a voltage that spikes, that quickly rises, overshoots, goes above 0 millivolts, that's what overshoots means, and then comes down again with a certain time course. That can be really quick, like in our nerves. The action potentials last more than a milli or 2 milliseconds, perhaps. Really fast. Okay? There are other action potentials that are longer lasting, so they can take longer to turn off. And those would look perhaps something like this. So this is going to be a mammalian action potential. An action potential in a cell like a snail or a squid, and the squid is the preparation where all these things were discovered for the first time in the late 1940s and early 50s by two guys in England and other people, and they found those action potentials look just like that at the beginning. So they need a little help here to bring you up above what? Threshold. Then they come down and undershoot. So this is due to a potassium influx. There are potassium channels there. You see? This would be a squid or crab, snail, and many of our actual cells also produce these types of action potentials. Okay? But these are the ones that typically in the book you will see these kind of things. Then, yes, sir.
Are the ones that only like rely on sodium channels, are those faster than the ones that have potassium channels?
Thank you.
No. The rise time here depends really strictly on the properties of the sodium channels, how fast they open when you change voltage. And these sodium channels are nearly identical. They're very similar. There are a few amino acids difference here and there, but PTX sensitive, the prototoxin sensitive sodium channels look very much the same, no matter where you look. And that is the reason why we study these kind of animals instead of doing everything on mammals. First of all, people don't want to kill mammals, and going through all the regulations and hoops to do research on animals is a real thing. While invertebrates, people without a spine, animals without a spine, but they are much easier to deal with, and they're simpler, they have fewer cells, they're typically larger. There are lots of advantages of using animals like that. And that's where these things were discovered, but now we know that the mechanisms are the same, and that's why we continue using these kind of animals to do research, because a lot of things are the same. So, as I said, the rise time here, this part, is very similar. It would be half a millisecond, whatever, but not much. So in the potassium channels and the inactivation have very similar kinetics. So typically people will, when they write models with computers, they make the inactivation and the potassium channel activation very similar because of that. So the speed will be the same. There's another difference that we'll talk about it soon, in terms of conduction of it, or of an impulse along the nerve. That's the difference. Okay, and then in places like our heart, in other neurons in the central nervous system, an action potential will look like this. There's, you probably understood, but not by much. So a long action potential, long lasting. And that's the typical thing that you see in the pacemaker of your heart, which is not a nervous tissue really, it's modified muscle, but behaves very much like neurons, in the sense that there are sodium channels that turn on and that stay on for a long time. And there are calcium currents as well that turn on. So you have a mix of channels there. So it's always produce decoordination and sustain it. And then potassium channels turn it off, inactivation in the whole. Exactly the same mechanism as in these action potentials takes place, but slowly. So this is a single action potential. Okay? What you will see, and I have drawn once already, is something that we call bursting, where the cell is depolarizing. Okay? And then on top of that depolarization, polarizes, and on top of that depolarization, you may see that. This is a graded potential that I've been mentioned before. And it's called a pacemaker potential, or sometimes a plateau potential if it stays long for there's certain very specific definitions about it, but like that, you know. Then it's going to come down, and it may come back up and spike again. A burst of action potentials, so these are the action potentials. And this is the pacemaker potential is going to reach itself, like in the heart. Okay, except right, the heart is like in motor neurons that drive the muscles that make us walk. So this rhythmic activity is driven by cells that do this kind of thing. They use that rhythmic behavior, right? So the envelope of the voltage of those cells will be at the same timing as you're walking, and then they spike a lot at the top to indicate to muscles and other neurons activate or contract this muscle. Okay. Right, so there's something else. All right, so let's go back to the molecular structure of an ion channel.